Thank you very much for this kind invitation to come to here. It's my second visit to this wonderful city of Krakow, and this time we meet to discuss about what exists in physics, and of course among the most prominent questions is about quantum mechanics and about the quantum mechanical wave function, or more general the quantum state. So my title is about the existence of the quantum mechanical wave function. Of course, in a naive sense, it exists. When we work on it, we do calculations. But the question is whether this wave function has really an ontic interpretation. It's out there. It corresponds to reality in the same way as an electric field, or whether it is more something like information or about knowledge. So in my talk here, I have these three sections. I first go to quantum mechanics and describe some of the essential features. An important aspect in answering this question is, at least in my opinion, the quantum to classical transition. So how can we understand that the classical world, I mean, you are sitting there on definite places, you're not smeared out, how this emerges from the quantum theory, and in a modern point of view, this is the topic of decoherence. And because I myself work mainly in quantum gravity, I'd like to draw some lessons from quantum gravity, at least from our present knowledge of quantum gravity. And I think it has some bearing on the questions. I mean, if you work in quantum gravity and on quantum gravitational states, I think you have a definite opinion on the existence or non-existence of those states. Now, as Dirac, for example, in his famous textbook, opens his first chapter with the words about the superposition principle as the central feature of the theory, let me put it that way. So I have subdivided it into a kinematic aspect before you talk about time, and a dynamic aspect. So let psi 1 and psi 2 be physical states, then alpha psi 1 plus beta psi 2 with alpha and beta complex numbers is again a physical state. And if you have more than one degree of freedom, this leads to the notion of an entanglement between systems, or Verschränkung, as Schrödinger called it in 1935. And this is, of course, now a standard topic of investigation in quantum information theory, quantum optics, and other fields. Of course, this has to be consistent with the time evolution, and we have the Schrödinger equation as the dynamic equation that gives you the propagation of the state. So when it's linear, the sum of two solutions is again a solution. But this means that classical states, for example, where you see me here localized and not smeared out like a Schrödinger cat, they form only a tiny subset in the space of all possible states. So why? Why do we not observe also in the macroscopic regime those non-classical states? Let me quote Schrödinger, who put it very sharply in 1935 as follows: I would not call that one, but rather the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought. By the interaction, the two representatives or psi functions have become entangled. Another way of expressing the peculiar situation is the best possible knowledge of a whole does not necessarily include the best possible knowledge of all its parts, even though they may be entirely separate. Of course, this was initiated by the famous EPR paper, which had appeared in 1935. And if you read the correspondence between Einstein and Schrödinger, you see how these issues arise in the discussion. So, for example, the Schrödinger cat first appeared in the letter of Schrödinger to Einstein before it was published in print. Now the superposition principle has been tested in, thousands of different ways. So we consider it as really as a well-founded and well-established principle, in spite of the quote by Penrose that we heard in the morning that there should be something wrong about that. We can perhaps discuss this. For example, the binding energies of atoms and molecules, for example, helium, cannot be understood without entanglement. And this was recognized already end of the 20s, that if you don't take into the two electrons in the high helium atom, if you don't take into account the entanglement, you do not get the correct energy eigenvalues. Then there are many experiments about, for example, the Vienna experiments, the fullerenes, C60 and C70, also more complicated molecules. I'll show you an example in a minute. There are these welcher Weg or which path experiments where you entangle intrinsic atomic state with the atomic momentum. And you can create entanglement of photon pairs over huge distances. So this summer there appeared a paper by Chinese colleagues where they claim they have measured or created entanglement between two photons separated more than 1,200 kilometers and one in a satellite. It's hard to imagine, but this is what they did. You have superpositions of macroscopically different currents in squids, and also in particle physics it's important. Yeah? The concept of neutrino oscillations or the superposition of K-mesons is an effect of entanglement. Now, this is one particular example, an impressive one, now already more than 10 years old. So they managed to superpose this heavy molecule with this name, which is a biomolecule, so if you find it in your blood, through a double slit, well, it's a bit more complicated, but through a slit to interfere with itself and to create interference patterns, which you have here. So these are the interference pattern of this tetraphenylporphine. Also, it has been done here with the fullerenes. So these are impressive examples, and there seems to be no fundamental limit to the test of the superposition principle yet. They are even speculating in quantum optics about doing this with a virus, to have one virus superposed with itself going through a double slit. But, of course, there is the famous or infamous measurement problem that for many decades causes the debate about whether the wave function exists or not, or whether it's fundamental or not. And it was already sharply put by John von Neumann in his famous book of 1932. So von Neumann decided to describe everything, both a system and an apparatus, in quantum mechanical terms, because also the apparatus consists of atoms, so not having a separate description. And so here the system states are called n, they are supposed to be measured, and the apparatus state, maybe a classical pointer, they are called by the capital phi. So if it's switched off, you have a phi naught, and if it's switched on, then if n is measured, phi somehow depends on n. For example, if you have just two spins, spin up and down, so n can either be plus 1/2 or minus 1/2, and then the phi could, for example, then point either to the left or to the right. So far, so good, but now we have the superposition principle, and this tells us that, okay, you can start with a superposition of n, for example, not with spin up or spin down, but maybe spin right, say, which is a superposition of up and down. But what happens then is the following: because of linearity, you see that each single component then becomes correlated with n, and you have a sum over different pointer positions. That is, this microscopic superposition, which looks harmless, is promoted to a macroscopic superposition in the formalism, which no longer looks harmless because you don't see it in the laboratory. So von Neumann concluded by this that you have to modify the theory or to extend it more properly, so that in measurement situations the Schrödinger equation no longer holds. That is, the superposition principle breaks down, and that you have a so-called collapse of the wave function. So when you look at the system somehow, then this superposition collapses to one component. Now, it has taken quite a while to see that there is at least a partial answer to this problem. I mean, not a final answer, but a partial answer. And so Zeh in 1970, he remarked that actually macroscopic systems in quantum mechanics have a very sensitive coupling to other degrees of freedom. And these other degrees of freedom are usually called environment. It means irrelevant or ignorable degrees of freedom, but they are not ignorable in the sense that they generate an entanglement because of their huge sensitivity. And you can give numbers about this sensitivity. So if you have the superposition from the previous transparency, which is this one, and you add an initial state of the environment, so imagine we have this glass of water as a macroscopic system, which is maybe in a weird superposition, and the environment are the gas molecules here in the lecture hall. Yeah, they, of course, are not under control, but they are there, and they are described in quantum terms. And they now also become entangled, yeah, because if a gas molecule arrives, it scatters off, and so the scattered state depends on the location of this object. So this looks even worse now, but the important observation is that what we really see is only the apparatus and then the system, but not the gas molecules here. So everything that you can observe can be derived from the so-called reduced density matrix of system plus apparatus, which I call here rho S and apparatus. And if we assume, and this is the realistic case, that different environmental states are roughly orthogonal, because otherwise they could not see the location of the system, then if you calculate this straightforwardly, the density matrix is approximately diagonal. And that is, it looks as if there were no interference terms anymore between the different ends, say between the two different spins. Only probabilities remain. So only this Cn squared. So you could say the interferences exist because they exist here in this global state, but they are not there where you look at. So this is what then leads to decoherence. It was only called decoherence much later, but you could define it as the irreversible emergence of classical properties through the unavoidable interaction with the environment. And the objects then appear classically, although they have no intrinsic classical nature. Yeah? So everything is described in terms of quantum theory with wave functions, but they appear as if, under this situation, as if they were classical objects. So in the early years, there were not so many developments, mainly work by Zeh and Šurek, who did that, but we have since 1996 experimental tests, and in the Nobel Prize description of Arost and Vineland, decoherence was mentioned as one of the important things they discussed, but this was after 96, and this Nobel Prize was around 2012. So here you see some experimental results. This is from this paper. And so what do you see here? This is again these Vienna experiments. So you have this, say, fullerenes, you superpose them, but then you introduce step by step an environment, for example, by bringing in gas into the cavity where the molecules are, or heating them up so that photons escape. And what you see here on this axis is the visibility of the interferences. And here to the right, you see the pressure of the gas coming in, which leads to decoherence. And so this blue curve is the calculation, and these dots are the measured values in the experiment. Here you see a similar situation, but not with bringing gas in, but heating up the system, so that you also somehow get rid of the information of the interferences. So it's about interpretation of quantum theory. So what are the options that we have? I mean, we cannot say that this is a final solution because we still have this issue of having here this globally entangled state together with the local classicality. Now, and people have different opinions on that, and I'm sure this will be also reflected perhaps in the discussion here and on the question of the conference and what exists in physics. So these are alternative opinions or possibilities. So the first is that the superposition principle and the Schrödinger equation, they are universally valid. They just they are valid all the time without exceptions. And this leads to what you call a many worlds interpretation or average interpretation, that is in this situation where you have pointer to the left and pointer to the right, both together. Then if decoherence occurs, then you mean to have two different worlds. It's a metaphor, two different worlds. It's one quantum world, but two components that do not know from each other. So but they are both there. And only if you restrict to one of them, then you can talk about probabilities. Yeah, so this famous example with the Schrödinger cat, you have certainly heard about this, that a dead and a live cat, they simultaneously exist in different so-called branches. So in the morning we talked about the now, for example, and the question whether we can define the now or not. In a sense, this whether you are in this branch or that branch is perhaps a similar issue that we could discuss. You know, it's not determined by the theory. The actual outcome is not determined. Or you go back to what von Neumann already suggested, that you must modify the formalism to accommodate a collapse of the wave function. And then only the dead cat exists, or the live cat with probability 1 or probability 2. No? Or then it means I'm either here or there, but not smeared out. But the important thing is you must modify the linear, or abolish the universal validity of the Schrödinger equation to achieve that. And there are various groups in the world looking for such collapse equations, also looking for their possible experimental significance. And we had this talk on Penrose in the morning, who is very suspicious about this superposition principle, and he's also involved in one of these experimental groups to see whether you can have a collapse introduced by the gravitational field. That's his idea. He wants to have a collapse actually to avoid this interpretation. I mean, if you allow, because we had this talk on Penrose in '96, there was his birthday conference in Oxford, and I remember he was given the last talk. As long as he wished, it was 2 hours or something, and he was then very explicit about his interpretation and about his Platonist ideas, and he said, okay, he can never accept this here. Yeah, these are the consequences of our present formalism, but he can never accept that because it's in contradiction with the idea of having this Platonist world out there. There cannot be different boundaries. This is why he looks for this alternative. No? So it's a clear statement. You can also change the kinematic structure, for example, having additional particle positions. The Bohm theory, I think, is this. Is the standard. No, the standard example here. Although this is very close to the first one, the Bohm does not touch the linearity of the Schrödinger equation. Or you say, no, we don't care. We only want to describe experiments. Wave function is perhaps only about information, and then you arrive at these epistemic interpretations, which of course you do not finish your way. You stop at some point and you say, no, I only want to make calculations. So this is certainly not my point of view. So my point of view is that we should take seriously these alternatives. What about gravity? And this brings me to the last and third part about quantum gravity, which is certainly a theory under construction. But there are motivations for doing so. And one motivation that involves the superposition principle as a central aspect, you can find here in this quote by Richard Feynman. It's from a famous conference in Chapel Hill in 1957, which is maybe the first conference where problems of quantum gravity were really discussed. And they were already all there, those problems. And Feynman considers this Gedanken experiment, which is a Stern-Gerlach type of experiment. So you have a spin half particles deflected in an homogeneous magnetic field. They spin up, it's deflected upwards. If spin down, it's deflected downwards. But if it's spin right, then it's in a superposition of up and down. And Feynman imagines there is some interconnection between the counters and a macroscopic ball, such that if the spin is up, the ball is moved upwards, and if the spin is down, the ball is moved downwards. That is, if you have spin to the right and you have the superposition, you would have the ball in a superposition of up and down. Well, it's a kind of Schrödinger cat type experiment. And the macroscopic ball has a measurable gravitational field. So you would have also to invoke a superposition of a gravitational field. Feynman used the following words: if you believe in quantum mechanics up to any level, then you have to believe in gravitational quantization in order to describe this experiment. It may turn out, since we've never done an experiment at this level, that it's not possible, that there is something the matter with our quantum mechanics when we have too much action in the system or too much mass or something. But that is the only way I can see which would keep you from the necessity of quantizing the gravitational field. It's a way that I don't want to propose. But for example, Roger Penrose is a person who wants to propose that, just that. Just in that in such a situation where you have a macroscopic gravitational field, then you have a collapse. And this is what Feynman does not want. But this is the issue. And it's a question that, of course, we have to decide in physics about experiments at the end. And I'm surprised to see that now people in quantum optics discuss actually the possibility to prepare such states, which they call GravCat states, gravitational cat states. So this would be a somewhat laboratory entry to quantum gravity. But let me go to something older and to one approach to quantum gravity, which is certainly not the only one, but the most conservative one, because you directly quantize Einstein equations in the metric formalisms. That is, you do not go to use another formalism, you do not go to string theory. I could, in the discussion, also tell you about string theory. And this is an approach that actually was started by Rosenfeld in 1930, and then was elaborated by Dirac and Bergman, and in the 1960s then by John Wheeler and Bryce DeWitt. And what did they do? They wanted to find a Schrödinger type of equation for the gravitational field. So how do you do that? If you remember what Schrödinger did in 1926, he wanted to have a wave equation because of the Breuil's idea. So he reformulated classical mechanics in Hamilton-Jacobi form, and then he devised a wave equation that gives back Hamilton-Jacobi in the classical limit. Or in other words, like going from wave optics to geometrical optics. And this is how he found the Schrödinger equation. It was not derived, it was somehow devised or guessed at. And if you do the very same for the gravitational field, for Einstein's equations, you find this so-called Wheeler-DeWitt equation. So this is unavoidable unless you really want to have a breakdown of quantum theory of the superposition principle, want to invoke collapse or something like that. Okay, it looks complicated and you do not need to understand the details for my talk. It's just to show you there are some equations that have a form, a Hamiltonian on the wave function is equal to 0, and also some other constraints. Actually, we heard about the constraints also in the morning about the initial value problem. These are the classical constraints that you have to fulfill for your Hubble surface to have the evolution, the unique evolution. And these are the quantum version of these constraints. And the psi only depends on the three-dimensional geometry, not on the four-dimensional geometry. This HAB is a shorthand for the three-metric. And yeah, this is gravitational constant, Planck's constant. This depends on this HAB. This is three-dimensional Ricci scalar, cosmological constant, not important for this talk. Important is you have some equations that have the form H psi equals 0. And the most important consequence is that time has disappeared. Maybe we discuss also about the existence of time in the course of the conference and maybe in tomorrow's discussion session. And time has disappeared, and John Wheeler has explained it on the blackboard that it's not something, not a miracle, it's a consequence of quantum theory, because if you have, say, quantum mechanics, you have a particle with a trajectory here, and if you quantize, the trajectory is gone. You know that. But of course, you have the absolute time in quantum mechanics. In Einstein's theory, the analog of the trajectory is the whole space-time. But there's no additional absolute time. So if you do the usual quantization, Heisenberg, uncertainty, whatever, then the space-time is gone in the same way as the trajectory is gone. And here you only have the positions, and here you only have the three-dimensional geometries. Yeah, so this is because it's a bit unexpected, perhaps. It's called the problem of time, that time t has vanished from a formalism, and I should emphasize that this is no peculiarity of the Wheeler-de Witt equation. It's a consequence of all theories that classically do not have an absolute time, because then upon quantization, the space-time disappears. If you believe in standard quantum formalism, no collapse or the like. And so it holds also in loop quantum gravity and probably string theory, although there the situation is a bit more complicated because of the mathematics involved. The Wheeler-de Witt equation, if you look more carefully into it, has a structure of a wave equation like the guitar string. So if you look more carefully into this kinetic term, there is one part that has a different sign than the others. And so this gives you an intrinsic dynamics, but an intrinsic time that is constructed from the three-dimensional metric. Yeah, I skipped those other. Or I should mention at least this, because we are talking about also probabilities. In quantum mechanics, of course, central issue is the probability interpretation. And this is why we have a Hilbert space structure. In particular because of the conservation of probability in time, which is unitarity. But if there's no time, of course, it's not clear what happens with this. Do we really need a probability interpretation if there's no time? Or do we only need it in the semi-classical approximation? Even more drastic becomes the situation if we apply this to the universe as a whole. Now, why should we do that? This is certainly a big step from the laboratory to the universe. But if you listen to Gell-Mann and Hartle, they once claimed that quantum mechanics, even the standard quantum mechanics, is best and most fundamentally understood in the framework of quantum cosmology when you apply quantum theory to the universe as a whole, because then we have to deal with the quantum theory of closed systems. We don't have to rely on external measurement agencies. Quantum cosmology is a consequence, if you believe, of the universality of quantum mechanics. Of course, one does not have to believe that. You could have a collapse, but the superposition principle and all the experiments, Decoherence suggests that the quantum theory has these universal features. And then, of course, the universe as a whole is the only closed systems in a strict sense. So you have a system coupled to environment, and eventually you arrive at the universe as a whole. But then you need a quantum theory of gravity, because at cosmic scales, the gravitational field is the most dominant interaction. So to describe quantum cosmology, you need quantum gravity, but conceptually quantum cosmology is first. This is an example that I already calculated some years ago, just to demonstrate that at this level you can do quantum cosmology as you do quantum optics, for example. You can solve the equations, you can construct wave packets, you can look how they, whether they assemble the classical trajectories or whether they are smeared out. So this is a simple example of the Wheeler-DeWitt equation, which comes from a cosmological model of a Friedmann universe with a field in it. And the classical solutions are Lissajous ellipses here. This is the size of the universe A, the scale factor, and this is the matter field that is there. And the classical solutions are half, because the scale factor starts at A equals 0, half ellipses. And you see here you can construct wave packets by solving this that follow this. So you can, in a sense, treat the quantum cosmological wave function as you treat the quantum mechanical wave function. Of course, there is the issue of the quantum to classical transition. It becomes more severe because the universe and space-time are what we think is the most classical entity in nature, and it's a prerequisite for having, say, quantum theory on top of the classical background. So if you quantize that, I mean, where is the classical background and everything? Now, in quantum gravity, there are many things that are not clear. So people working there rely very much on analogies with known physics. And one analogy is molecular physics and the Bom-Oppenheimer approximation. In molecular physics, you have the situation, if you want to solve Schrödinger equation for a complex molecule, that this is very difficult to do. So you can do the following. You can say, aha, we have the nuclei, they are very heavy. And we have the electrons, they are much, much lighter. So let us separate the scales. Let us first neglect the motion of the nuclei, because they are so heavy, and just solve the problem of the electrons in a fixed, on a fixed configuration of nuclei. And this you can also do here, because somehow the gravitational field plays the role of the nuclei. It has a scale with it, so-called Planck mass, which is the scale of quantum gravity. And so that this metaphorically, it moves slow and can be then considered as a fixed background. And then you arrive at quantum theory in a fixed background. But then at the next order you can, or have to, somehow use the dynamics of the gravitational field. Okay, so this looks a little bit like mini formula, but what is done, you have always the same constraint equation, h psi on 0, and here you have what you consider here a formal background, the Friedmann universe and a field, and here you have inhomogeneities describing, for example, gravitational waves or density fluctuations. And this is the full equation, but this is very complicated to solve. What you can do in this Bom-Oppenheimer is you can make the following. I mean, you can have an ansatz, the full psi is psi naught and the product of all the psi n. And if psi naught is of that form, then you can derive just by manipulations for all the psi n Schrödinger equations. Now suddenly a time t has emerged from the timeless equation. So where does this time come from, t? Now the time is just comes from a directional derivative in the configuration space, like the limit of geometric optics from wave optics. There you have fundamentally wave optics, just waves interfering, but in the limit, then you have light rays. And the formalism is well known, it's the Iconal equation, all that, and more or less this is translated into the language here. So it's not that you invent here a new formalism, it's somehow that you use the analogies and the results from standard physics. Yeah, so decoherence in quantum cosmology then is an important question, because you have now arbitrary superpositions of the gravitational fields and matter states. So how can we understand the approximate classical nature of the universe? And at least within some model calculations, you can do that. Yeah, and just to have one example, and also with an analogy. You see always analogies in molecular physics. You have the following, you have the chirality of molecules, say of sugar. The Schrödinger equation is parity invariant, so it does not distinguish between left and right. So if you solve the spectrum of the Schrödinger equation, of course you have parity invariant states. But what you observe, for example, with sugar are superpositions of energy eigenstates, which are chiral. So you have this double well potential, so the ground state would be smeared out like that. The first excited state would be like that. But for a chiral molecule, you have a superposition of them, so that it cancels here, and for example, the molecule is here localized on the left part. This was a miracle for the founding fathers of quantum theory, and it's also known as Hund's paradox, because Hund in 1927 described that. One later learned how this comes about, namely by the interaction with other degrees of freedom. With sugars, you have optical activity, so there's a strong interaction with light. And if you take that into account, you can understand the decoherence that in spite of having a superposition, you have then that this B is in the left or on the right. And you can understand this quantitatively. For example, if you have very small molecules, you can understand why there you don't have this chirality, that they really have this transition from left to right, like the ammonia maser, ammonia molecule, NH3, which really goes from left to right. And in quantum cosmology, you can do the same. I have somehow been quick here. We have made this, one makes this ansatz with the e to the I as naught. There we have the imaginary unit. The imaginary numbers are very important in quantum mechanics. But the Wheeler-DeWitt equation is a real equation, so not like the Schrödinger equation. So you would expect superpositions in the same way as the Schrödinger equation is invariant under this parity transformation. The Wheeler-DeWitt equation is invariant under going to a state and its complex conjugate. But also here, you can have a symmetry breaking like with the molecules, that you can write down a real solution, but you get the decoherence between e to the I as naught and e to the minus I naught as naught. If you go to some calculations and in analogy to this here. And then you can see that, say, for our today's universe, if you put some numbers, the exact numbers are not important, that you get an amazingly small factor that describes a deviation between from the classical behavior. So it's really, at least for a big universe, very classical to a high degree of accuracy, as of course we would have expected, otherwise we would not believe our calculations. Now, having done this, one can also study the emergence of structure out of quantum fluctuations, and this is what is done these days in the context of the inflationary universe. It's not so that the inflationary scenario is proven in a strict sense, but it's believed by many cosmologists as the most natural one. Okay, again, not by Penrose. And we can discuss this because here this has to do with different aspects than with the solution of the horizon problem, for example. Now, according to this scenario, there was a quasi-exponential expansion very early, about 10 to the minus 34 seconds. The seconds is missing, sorry, after the Big Bang. And then there was a quantum, the matter degrees of freedom, they were in what is usually assumed in a quantum vacuum state. And then there was a quantum to classical transition, and the result eventually were these stochastic features of the cosmic microwave background. But of course, as a theoretical physicist, one would like to understand how this quantum to classical transition proceeded, not just assuming it as is done maybe in astronomy. And so this, again, is an application of the process of decoherence, and some time ago, together mainly with David Polarsky and Alexei Staubinski and also a student. We have investigated this and shown how this proceeds and to which accuracy, and found that actually these fluctuations really behave when it comes to the CMP like classical stochastic quantities, and then they can yield the seeds for the structure in the universe. So you see, quantum gravity, at least in principle, quantum theory, is needed to understand structures in the universe, at least if you believe in inflation. So if you look at those structures, so this is a famous picture from the Hubble Space Telescope, the ultra-deep Hubble field, all the galaxies. If this scenario is correct, this is the result of quantum fluctuations described by wave functions, by quantum states, after the process of decoherence has happened. So in a sense, by having also these structures and filaments of the galaxies which you observe, you see somehow the fate of quantum fluctuations. Yeah. I would also like to mention that in a certain sense, we already have one observational test of quantum gravity. You always hear that quantum gravity is not tested and it's probably never testable. If this inflationary scenario is true, then the point is, according to all the standard textbook calculations, you not only have to quantize the scalar field, the matter part, but also the metric fluctuations. You have to combine them in a so-called gauge invariant way, so metric part and matter part. And only those together give you the power spectrum that you observe. This is the famous picture from the Planck satellite here. Yeah? So if you did not want to do that, if you would like to leave out the metric, you would not arrive at that. So in a certain sense, this involves quantum gravity, although only at a linearized level. But if you write down the metric in a form with A's and A daggers, creation and annihilation, so what else than quantum is it? So it's an indirect test. I mean, there was some excitement a couple of years ago with the BICEP 2 experiment at the South Pole that, I don't go into the details, but it would have meant that they would also have measured so-called tensorial degrees of freedom, the gravitational waves, but in the inflationary scenario, they are created as gravitons. So this would have been a more direct test even of quantum gravity, because you cannot do this in any classical way. In inflation, if you have only classical gravitational waves, they would be diluted. You have to create gravitons. And all the effects that you have here, they are proportional to h bar. Unfortunately, people often set h bar to 1, and so you don't see this. But if you put in the units, you see that all these effects here disappear for h bar to 0. Yeah, I'm approaching the end. Yeah. So the interpretation of quantum cosmology is certainly more severe than in quantum mechanics, but in a sense it reflects the same problem. Almost all approaches to quantum gravity preserve the linear structure of quantum theory and the strict validity of superposition principle. Even string theory, which is very complicated with all these many dimensions and supersymmetry, and you have to learn a lot of mathematics, but this part is very conservative. It's just quantum mechanics 1, superposition principle. And the main interpretation of this is the average interpretation, with decoherence as a key ingredient, because in quantum cosmology it's hard to imagine the alternative. Of course, you can imagine also some collapse, but how should it come about? Bryce DeWitt, in his pioneering paper of the Wheeler-DeWitt equation, expressed it in the following way: average view of the world is a very natural one to adopt in the quantum theory of gravity, where one is accustomed to speak without embarrassment of the wave function of the universe. It is possible that average view is not only natural, but essential. Yeah, and I think I only have 2 slides, so if you allow, go to the 2 slides. So at a fundamental level of quantum gravity, it seems there is no need for the probability interpretation, because we don't have time, and it's not so clear what is the probability of this or that universe. But time and also observers with them appear in the semi-classical limit, and we can there understand and do calculations how classical properties follow through decoherence. So the probability interpretation is needed only in this limit, and can perhaps be derived or at least understood in the way that, for example, Schurek has explained in 2005. At least it's consistent, the probability interpretation, with the formalism. I have not talked about the origin of direction of time, but this can be done too in this framework. And so, yeah, my question was, is the quantum mechanical wave function real, or does it exist? And so to be or not to be in this sense, we also had this in the morning, existence and being. And so I would emphasize in quantum mechanics, it's not only probabilities that we calculate with the help of the wave function, there are important structural issues. Yeah, in quantum field theory, this vacuum is determined by the quantum state and the particle concept, and we do not talk about the experiments with many vacua, or so it's structural issues. It's in a sense more the particle concept that is indirect compared to the quantum state. So it has dynamical consequences, and thus, in my opinion, cannot be pure knowledge or information. So it becomes even more important in quantum gravity and cosmology, where the probabilistic questions are less relevant and other questions are more important that rely on the structure of the quantum states. I mean, for example, all these things with the inflationary universe and the CMB and the origin of structure from quantum fluctuations. Because if this is correct, of course, there are alternatives to inflation, but if this is correct, all structure in the universe can be traced back to an early quantum state. This state undergoes a quantum to classical transition, which we then see the imprints in the cosmic microwave background. So my conclusion would here be the wave function exists in an ontic way, not epistemic way, but of course we are here to discuss this, and I'm happy to hear other opinions and to see the critical discussions of it. So thank you very much for your attention.